Hello everyone, welcome back to my channel. So back then I actually made two videos about how to get the cubic formulas, and both of them are actually pretty much only use high school algebra skills to derive out. And if you have never seen those videos yet, I'll actually put the links in the description so that you can check it out first. So today we're going to solve a cubic equation using the cubic formula that we have found. And the reason that why we would do that is because one of the viewers actually put a comment down in one of those videos and want me to actually give an example and to try to solve it using the cubic formula and see if we'll be able to get the same result. So here is the example. We have 4x cubed minus 108x squared plus 720x minus 1400 equals 0. So in this video, I'm going to solve with the regular way, which is by factoring as our first method, so that we'll actually see if we do it usually how we'll be able to get the answer. Then I'll use the cubic formula to help us getting the result and see if we'll be able to match them. Okay, so before we talk about the cubic formula, here on the right hand side of the board are actually some of the tools that we need in order to get the solutions for a general cubic equation. And I've labeled all of them, the P, Q, U, V, and this omega for our final form X, which is going to tell us the solution of the general cubic equation, where A, B, C, and D are just the coefficients of the cubic expression. So if you're ready, we're gonna start with the regular way first. So when we usually do it with factoring, of course we would like to see if there's anything we can factor out from the expression. So we see that the coefficients are all multiples of 4. Of course we can reduce it, and then we will be able to get the expression x cubed minus 27x squared plus 180x minus 350 equals 0. And we're going to use this as our original equation later on for our substitution for our cubic formula. Anyway, so for first method, we're going to do even high school students will be able to do, which is factoring. And to do that, we will just take again the leading coefficients. In this case, it will be 1, and then also the constant term, which is negative 350. And we're going to use what we call the factor theorem, or also known as rational factor theorem, which is if there exists a rational solution for x in the expression here, we will say that that solution must be in the form of q over p, where q will be some factor of the constant term and p will be some factor of the leading coefficient. And to do that, we just need to find out all the possible combinations and just substitute in until we get a value of x such that the left hand side has a remainder equal to 0. Or we can say that after substitute x with such value, the sum will turn into 0. So if we try all the possible cases, we'll actually end up with x equals 5 or x minus 5 being a factor of this expression, so that now we can actually use the long division algorithm to figure out the rest of the factor, which is x squared minus 22x plus 70 equals 0. So now for the first factor, we can say that one of the solutions is of course equal to 5. From the second factor, since it is reduced down to a degree 2 polynomial, in other words, it is a quadratic expression, we can use our famous quadratic formula to give us the answers 11 plus or minus square root of 11's square, which is 121, minus the leading coefficient 1 times the constant term 70, which is 70. So if we try to simplify or simplify everything inside of the radical, we'll end up with 51. So these are the three answers for the original equation that we have. And this is it for the first method, which is what most people would use. And keep in mind, now we're going to move on with the second method, which is using just the cubic formula with the equation that we have. Of course, since the original equation and the ones that we reduce are actually identical, well, nearly identical, except we just divide both sides by 4, which is a constant, so it won't matter whether we use the original equations as our standard A, B, C, and D, or the one on the bottom. But of course, it will be easier if we use the bottom for a couple reasons. First, the numbers are all reduced, so we don't have to calculate with all the multiples of it. And second of all, now we actually get the leading coefficients B1, so that now we know that A is equal to 1, and it will actually help us reduce even more in our expressions. So before we move on and substitute in, let's keep in mind that we should end up with 3 solutions, and those 3 solutions should be matching with the solutions that we found using a different method, which is the factoring method. So I'm going to write the solutions, or the correct solutions, on the right hand side here, which will be 5 and 11 plus or minus radical 51. Okay, so here we go. To do the cubic formula, which actually ends up with the form x equals negative b over 3a plus omega to the k power times u plus v over omega to the k power, where omega is referring to the principal third root of the non-principal third root of the unity 1, meaning that we're going to take the first complex root of complex cube root of 1 be our omega value, where u and v are some values in the expression of p and q, where p and q again is following from the a, b, c, and d. We first need to figure out what p and q are. So in this case, we will have p is equal to, let's see, we have 3ac, where a is 1, so we have 3 times 1, which is 3, times c, which is 180, minus b squared, where b squared is negative 20, the square of negative 27, so let's write it as 27 squared, over 3a squared, where a again is just equal to 1. So now we can just reduce it to get 180 minus 27 squared, where 27 is just 3 to the third power, so we'll have 3 to the 6th power. So divide by 3, so we still have 5th power, which is equal to 243. Then we subtract it, we get negative 63. So this is our p value for this equation. Next, we'll figure out what the q value is. Then again, we just substitute in On the denominator, we have 27 times a to the third power, where a is again 1. So we have 1 cubed, which is 1, times 27 is 27. On top, we have 27 times 1 squared, which is 1, times d. In this case, d is negative 350. Minus, we have 9 times a, which is 1, times negative times b, which is negative 27. So I will bring the negative to the front, and then times c, which is 180, plus 2 times b cubed, and again b is negative 27, so that cubing it will still be negative. So again, we'll bring the negative in the front and change the sign. Then if we reduce it, we will get negative 350 plus 9 times 180 minus 2 times 27 squared. And that is going to give us, let's see, we have negative 350 plus 1620 minus 27 squared is 729. And then multiply by 2 to give us 1458. Then if we put the subtraction signs together, we get 1808. So if we subtract it, we get negative 188. Good. So let's erase all the math here. So to leave the result only negative 188. And that's our q value. Good. So now as we have both p and q values, we can substitute into u and v to figure out what u and v are. Then for u, we have the cube root of everything inside, where inside we will have 2 in the denominator. We have negative q, and that is positive 188, plus the square roots of the following expression. We have q squared, and again, that will be 188 squared plus 4 times p to the third power. And again, p is a negative value, so p to the third power is also negative. So I'll bring negative out to get 4 times 63 to the third power over 27. So let's try to simplify it. Let's see, what can we get? So we can definitely reduce the 2 here. So the first term turns into 94 plus inside of the square root. So inside the square root, the 2 becomes square root of 4. So we need to divide 4 for both terms inside of the square roots, which turns into 94 squared minus the 4 is cancelled out. Good. We have 63 cubed over 27. And again, 63 cubed is the same as 21 cubed times 3 cubed. And then the 3 cubed will cancel with the 27. So we ended up with 21 cubed here. So in fact, if we try to calculate everything inside of the square root, we will get negative 425, which means if we try to reduce it, we will get the imaginary unit, and we will also get the 25 out. And if we factor the 25 out, so we'll get the 5 outside, because again, the square root of 25 is 5. Then divide by 25, we will end up with 17 remaining inside the square root. Now v, in here we actually have the expression here, and we see that we just need to flip the sign. So we will get the cube root of the quantity 94 minus 5i radical 17, like this. So that now everything is ready. We have both u and v. We can now substitute into our expression x, so that we'll be able to get our solutions. So our first solution will then become x equals negative b, and again b is the value that we use here in this second line, which is negative 27, meaning that we are double negative. It turns into 27 over 3a, where a is again 1. So we have 27 over 3, which is 9. Okay, good. Then plus omega is what we call the root of unity. And in this case, we're taking the cube root of it, so it'll be in the form negative 1 plus I radical 3 all over 2. And then we need to raise it to k power. So in this expression here, we say that k could be any integers. And in fact, in order to cover all the solutions, we will just take it to modulus 3 or into z3, so that now we just have 3 different answers, or 3 different what we call equivalent classes, or end up with different results, which are 0, 1, and 2. It's just like when we divide by 3 and then find out just the remaining part. And those remainders will actually, each remainder will actually yield a special solution. And it will be able to cover all the solutions if we use all different remainders. And each remainder will be different from another remainder. So we can now substitute in to get the following. So let's leave it as k for a moment. And then we're going to multiply with u, which is this right here. The cube root of 94 plus 5i radical 70. And then plus v, which is this right here. The cube root of 94 minus 5i radical 17 divided by omega to the k power, which is the reciprocal of this. But here is also one more trick, which will be used a lot in complex calculation, especially when we do complex analysis or doing play around with complex numbers. Which is when we think of the unity, the roots of unity here, we can just think the inverse will be same as the how should I put it? It will be the same as taking the power of the unity that the roots of the the power of the roots of unity that we have, subtract with the k value. So it is not easy to see, but what it meant is here we can also say that instead of dividing by this value here, we can just simply multiply. Let me put it down here. Is the same as multiplying the unity, the root of unity, raise it to the negative k power. And again, that's how we define the negative power. But that's but we can we will just now put another number right in the front of negative k. In this case, we're going to put a 3 here, and again, that is because we're having the cube root of unity, meaning that we have the third root of the unity. So, in other words, if we try to raise this third root of unity to the third power, we'll actually get back to the unity itself, 1. So by again the exponential rule, we can just put the exponents together to get 3 minus k. So for example, if we choose k to be 2 here, then instead of just divide the cube root of unity, the square of this value to the last term, we can instead multiply by 3 to the 3 minus 2 power, or the first power of this unity to the last term, and we'll be able to get the same answer. And that will be able to cover all our values. So that is, if we try to substitute in, let's say if k is equal to 0, we will get our first answer, 9 plus the cube root of 94 plus 5i square root of 17 plus cube root of 94 minus 5i times square root of 17. And if we substitute k equals 1, we will get 9 plus, now we have to substitute the omega, -1 plus I radical 3 over 2 times the first part, which is cube root of 94 plus 5i radical 17 plus, and again we will multiply the two copies of the unity here, so we will actually get -1 minus I radical 3 over 2 times cube root of 94 minus 5i radical 17. And that's our second answer. And last but not least, if we substitute k equals 2, we'll get our last answer, which is, now we have the second power of omega times u plus the first power of omega times v, which is like this. And that will give us all three answers. But now you may ask, wait a second, if we use the factor theorem, we can actually get the answers so nice and easily. We just end up with the integer 5 and even some fairly nice expression, 11 plus or minus just a square root of some integer, 51. But if we use here, we actually get something, first of all, looks very ugly because we have the cube root and then we have a square root of the cube root, and then later on we also have some imaginary units and stuff. What's going on? Does that mean that the cubic formula is wrong? How do we actually end up with something that looks totally different from what we have? Okay, so actually this is fine, because here is the deal. We can now, as we know the what's so-called correct answer using the factor theorem, we can now try to check whether we will be able to get the same whether we will actually get the same values for the solutions that we get using the cubic formula. So in fact, we will be able to get the first one is actually equal to one of the answers, 11 plus radical 51. And then the other two will match with the other two solutions, and I'll let you guys to check it. So in fact, even if the expression looks very ugly and it has containing it's containing the imaginary units, we can actually reduce it or combine them together so that we'll be able to yield with a very nice answer. Okay, and perhaps you don't agree with it, or you might question that, well, why are those two the same, or how are they like, how do we actually show it? I'll leave it as an exercise for you guys to figure out. And of course, if we get enough likes for this video, let's say if we get 400 likes, I'll just show you the first one, how we can actually show that the left hand side, this ugly expression, is actually equal to a very nice expression on the right hand side, which is 11 plus radical 51. Okay, and I'll just make another video to show the first one as an example of how we can actually convert it from something that's messy to something that is very neat. Okay. All right, that is it. So pretty cool, huh? If you enjoyed this video, don't forget to like. And if you want to find out more of my other videos, you can subscribe to my channel and turn on the notifications so that you won't miss any of my new videos either. If you have any thoughts or questions about stuff, especially for the stuff that we went through in this video, you can leave your comment below. But of course, you can also just leave anything down in comment if you want me to try to do it, or if you have anything that want to talk about. All right, I'll see you guys in the next video.